So in this lecture, we will learn about some real world cases. As it is discussed in logistic regressions, in the case of linear regressions also, we are discussing some real world cases for linear regressions also. Okay. So first we are choosing if our data set is imbalanced data. If our data set is a imbalanced data, I think all are about clear what is imbalanced data means. In this data, our data is not properly balanced. Okay, suppose balanced data for regressions mean what? It is well distributed. Suppose in a data, just see this thing in graphically. In regressions, imbalanced data means if a data is belongs to, suppose in data R belongs to R, suppose in this actually yi belongs to real number in regression technique. Okay, suppose our data that is we are using in training data, that is called pre-train, its data 90% of the data are belongs to, suppose it belongs to 0 to 1, it's like, and 10%, only 10% of this data is lies between, suppose 2 to 10. 90% of the data belongs to 0 to 1 and only 10% data is belongs to 2 to 10. Okay, so this kind of data set we call it as an imbalanced data. And what about the imbalanced data of our classification technique? It is the imbalanced data of our regression technique. Okay, and if we consider this data imbalanced data for classifications, then what will be that? Suppose in the classifications, what will yi will be the what? Yi that is belongs to natural number, or simple, no, it is not called a natural number, it is simply an integer value. It will take only the integer value. Suppose yi belongs to +1 and -1. If we see our D-train data set, among it 90% of the data belongs to +1 classes and only 10% of data it is belongs to -1 classes. This means what? It is not well distributed. It is not well distributed. Okay, so in such kind of, in classifications and regressions, in such kind of data is called the imbalanced data. It is also not well balanced, well distributed. Okay, in such kind of data is called the imbalanced data. So to handle this kind of imbalanced data, we are simple as KNN, as our naive Bayes, as our logistic regressions. Here also we are using upsampling and downsampling technique. And we are using upsampling and downsampling as our requirement. Okay, so to handle this, now come to the next concept, that is features important. How we are interpreted which feature is most important. So it is as trivial as logistic regressions. If you just revisit our logistic regressions series, then you can easily find how to handle the features important. So just write down features importance and its interpretability. and there have many models. We will see later of this series of lectures. They have many models. There we can predict which feature is important and which feature is not, but we cannot interpret it. We cannot give the reason behind it. When we learn about the deep learning, then we can see that we can easily find which feature is important, but we cannot interpret why this feature is important or not. And in some medical applications, this concept interpretability is very important, because we can interpret it. Why these features is important to our model? Why this count of output is coming from our model? This is very important thing. So feature important and its interpretability is very, very important in the world of machine learning. Okay. So simple as logistic regressions, here also we are using the multi-collinear. If collinearity, if it is not multi-collinear, if it is not multi-collinear, then our best features depend on the mode of WJs, norm of, that is absolute value of WJ. These features are depend on absolute values of WJs. So it is as trivial, simple, as trivial as our logistic regression. Okay. So same, it is as trivial. Linear regressions, the features importance of linear regressions and logistic regressions, which include the both are the same technique. Both are the same. So now coming to the concept of multi-class classifications. Now, case 3. So it is a simple regression technique. So here no uses in classifications. No multi-class classifications are used here. Sure. No multi classifications are used here. It is not useful here because it is a classification technique. Okay. So for this reason here multi-class classification is not useful. Now come to the fourth thing, that is features engineering. Here we can apply features engineering. Yes, obviously, as logistic regressions, here features engineering is most important thing. We will learn the features engineering in logistic regression series. It is how important you can see. If you have a nonlinear data set, simply we are using the features engineering technique. We can easily build a low latency system as our requirement. So it is most important chapter. Features engineering, the most important concept in the world of machine learning. So features engineering, or many authors call it as features transformation, is most important. It is as trivial of logistic regression. It is same as logistic regression. Okay. So in regression technique, or just you think in regression technique, we are using the for build a low latency system. Just remind this thing. For logistic regressions, similarly, these are both things are similar. Logistic regressions and linear regression, both the regularization concept, both are the same. So just remind this thing. For regularizations, we have the parameter lambda. Okay, if we consider our L1 regularization, if we just take the L1 regularizations, then if we increase the value of lambda, then what? Then our sparsity increases. Then sparsity of the model increases. If our sparsity of the model increases, means what? Means our less important features, weight vector of the less important features will be going to 0. So less important if I is less important if I is corresponding wj's. Wi is going to 0. Simple, not going to 0. Simple, if we taking the L1 regularizations, it will take the value 0 equals to 0. Okay. So if lambda increases, sparsity increases, means what? Our latency increases. Latency increases or latency decreases. Or low latency increases. Sorry. Low latency increases. Means our output to build the output of the model, it is low latency system will be easily built. Okay. Now coming to our fifth concept, that is we call outlier. Okay, just taking different color. Okay, now we're coming to the concept of outliers. So we can see in logistic regressions, you can just compare the linear regressions with logistic regressions. We can see in logistic regression, for handling the outliers, we are using the squashing technique. Squashing technique means what? We are simple using the sigmoidal function. We are using simple sigmoidal functions to build the squashing technique, and what is it is doing? It is the limiting the impact of our outlier. It limits the impact of outlier. It limiting okay, it limiting the concept of outlier. Now in linear regressions as well, there have many outliers. So just draw the picture. That is our x, that is our y, and in the end of the day we are finding the best fitted line or plane. If you have a outlier, that is here, then we are finding its distance from our predicted value, that is, it is called the sample. This is our predicted yi's, this is our actual yi's, and we are finding its distance. We want to minimize its distance. And how? By using simply to minimize. How it is minimized? By sampling the square of all these distance square sum. Yi means yi hat square over all I. Okay, we are just simply, this is means what? Actually this is called square loss term. This is actually square loss, but here impact of the outlier for linear regressions, because of the square loss, the impact of the outlier is so much. Here we are not simply we can see in logistic regressions, here we can using the squashing technique by using the sigmoidal functions to handle the impact of the outlier there, but here we cannot use some kind of things. So here outlier impact is so huge. Okay, now to avoid, how to control these outliers? Simple, we are using here the Ransack technique. Okay, here simple we are using called the Ransack. Ransack means what? This ran, this sack. Random, ran is stand for random. This A, SA is stand for sampling, random sampling consensus. This SA is called for sampling, and this C is stand for consensus. Okay, this is called the random sampling consensus. Now let's see what is this technique, what is the Ransack technique. So first we are having a training data sets that we called here T train data. Okay, and after training using the D train data, we are finding what? We are finding the optimal weight vector, that is called W star as vector, and W is not, that is the actually interceptor, means that is actually the scalar, and this is actually the vector. Now in next, what we find? Now we find the points, that is this find means what? Actually we are finding this, means we are finding a hyperplane. This is finding a line or plane or hyperplane, as you depend on our data sets. Sorry. Depend on our data sets. Now find the points. Now this is these vectors, these weight vectors finding means we are finding the line, plane or hyperplane. And after finding this plane, we are finding the points which are very far away distance from this called pi plane. This called it as pi plane. Now after finding this plane, we are finding the point that is very far away distance from our actual plane, from our predicted plane. This pi actually our predicted plane. That is, find the points which are very far away from pi. So how it is calculated? By simply calculating the distances, yi minus yi at. If this distance is increased, this means these points are far away from this. Now third, how we are calculating? Now in third step, we are simply remove this point that are the far away from our plane. We are simply remove this point as outlier. So remove this point. So now what will be our data sets? Let's just call it as our D train, D dash train. These will be our data set. Now these will be the main data minus our outlier. Okay, this will be the data. Now using this data set, again we are training the model. Now using this data set, again we are training our model. Again we are training our model. Train or build our model. Simple as you call. Now we are repeating this thing again. So now what? Now again using this model or training, we are finding the outlier. Okay, finding the outlier by using this technique, and then again we are remove this outlier from our from this stage, and again this training model, just repeating this technique, Okay, so here we are repeating this technique, so it is called an iterative technique. Okay, for this reason it is called an iterative technique. So to handle this outlier in the linear regressions, because here we cannot use some squashing technique or something else, so to handle this outlier, here we using this Ransack technique. This technique is called the Ransack technique, this iterative technique. Okay, now I think this kind of real world cases in natural world, in the natural data sets, if you see in real world data sets, then these will be imbalanced data, these will be either this data will be nonlinear separable data. There are the many cases data. So this kind of typically these kind of situations are typically these kind of situations you are seen in a raw data. Okay, I think it is clear how to handle these real cases for linear regression. Okay, if you had any doubt, please comment below. Okay, thank you.